Okay, hi everyone, welcome back. So another video about probability distributions. This is the last one I'm going to make in this series about probability distributions, data distributions. And this one is about the beta distribution or the beta distribution. I guess it depends where you're from and how you say it. But it's an interesting one, it's an interesting distribution. So the beta distribution is a continuous probability distribution. The standard beta distribution uses the interval from 0 to 1, so data values used as input for a beta distribution take on values between 0 and 1. It's used to model random variables of finite length, and it's suitable to model the behaviour of percentages and proportions. As such, you'll often see it used to model the probability of probabilities. So it can be utilised once we have a Bernoulli distribution, which would give us a distribution of successes and failures that can be interpreted as the probability of having however many successes we observed out of a total number of trials. And so remember, Bernoulli trials were like coin flips with success or failure, that type of thing. So recall, you note that the Bernoulli distribution, it can only take on discrete values of success or failure. So counts of success compared to the number of failures out of a total number of trials, for example. So however, the beta distribution being continuous can take on any value between 0 and 1. So if we want to work out the probability of observing a given success outcome, for example, rain occurring, when we know the success probability for that event, we would use the beta distribution. So for example, what's the probability of us observing rain today if it's rained on 70 out of 100 days? So we then think or calculate that it rains with a probability of about 0.70% chance. And we can use the beta distribution to calculate the probability of an event when we have some information about the volume or proportions of successes and failures. So the primary use of the beta distribution has been in Bayesian statistics, Bayesian data analysis, where it's used as a conjugate prior for the binomial and Bernoulli distributions. I believe it can also be used as a conjugate for the Gaussian distribution. So a conjugate prior is observed when the prior and posterior distributions you obtain from your analysis come from the same family of probability distributions. Okay, so the beta distribution has certain parameters. It has a shape and a scale parameter like a number of other distributions. However, the beta has two shape parameters. Alpha and beta is what they usually refer to as. And both of these parameters have to be greater than 0. So the shape parameters alpha and beta are calculated as alpha is usually k plus 1 and beta is usually equal to n minus k minus 1, where k is the number of successes from our trials and n is the total number of trials. Okay, so the alpha and beta parameters control the shape of the distribution, and adjusting the values of those alpha and beta parameters will change the shape of the beta distribution's probability density function, its PDF, and its cumulative distribution function, its CDF. So in addition to these, to make it I guess more confusing, in addition to having these alpha and beta shape parameters, the formula for the beta distribution, when you see it written down formally, it commonly contains the parameters a and b also, which are often used to denote the lower and upper bounds of the finite intervals, such as between 0 and 1. Okay, so changing these shape parameters changes the shape of the distribution. So the beta distribution is quite a flexible distribution, and that's kind of one of the appealing things about it. It's why it's kind of useful as a conjugate prior, because you can change the shape and get it to follow certain shapes that might be appropriate for the model that you're trying to use. So what I'm going to do in this video is demonstrate how to simulate data that follows a beta distribution, similar to what we've done in previous videos. And then what I'll do is then plot the PDF of the beta distribution using different values for the shape parameters alpha and beta, and then do a load of other plots just to show how changing the parameters of alpha and beta, changing the values of those two parameters, changes the appearance of the distribution, so you can see the flexibility that it has. I'll also use the PDF and CDF to obtain some probabilities for specific input values. So let's start off by importing some software libraries. I'm going to import NumPy as NP, pandas as PD, matplotlib.pyplot as PLT, scipy.stats as stats. We're going to use scipy to generate our random variable that follows a beta distribution. We'll also import Seaborn as well because we use the displot function from that, I think, in this video. So I'm going to generate data using scipy stats. We're going to use the beta method, so stats.beta, and invoke the random variables method that I've used previously, so RVS. So basically we're asking scipy to generate a variable of observations of random data that follows a beta distribution. And what I'm going to do for the beta, for the arguments for alpha and beta, we need things we need to specify when we use this beta method. So we've got to specify alpha and beta, a locus scale, the size of the sample we want, the size of the distribution we want, how many observations. And I'm also going to set a random state. So I'm going to set a random seed equal to 1, so this can be replicated, this kind of data. So I've set alpha to 31 and beta to 21. I've just kind of arbitrary numbers to use, really. So the locus scale are 0 and 1. They're the kind of start and end points of our scale, and that's for 1,000 data points. So we've now got this object called beta underscore var, so beta variable is what I've called it, and it consists of 1,000 data points, and the distribution of that variable follows a beta distribution with the shape parameters alpha equal to 31 and beta equal to 21. So let's plot that. Use Seaborn to plot that distribution. So firstly, let's look at what it looks like if we I've just invoked the SNS, the Seaborn displot method, and it's plotted the data as, remember this is a continuous probability distribution, but it's plotted as a histogram, so it's used its own kind of defaults to choose a bin width that it thinks is most appropriate, and it's plotted it like a discrete probability distribution there. Note that the values on the x-axis are all values that fall between 0 and 1, as is typical for the beta distribution. But we can also, I'll run the same thing again and just ask for a KDE plot so we can see like the continuous version of what that looks like. Okay, so on the y-axis here we got frequency counts, and this time on the y-axis we've got the actual density. You'll notice the values are different. This might seem a little bit strange because this is like it's kind of a kernel density estimate. It's given us the idea of the densities, the probabilities essentially. You might recall, I'm not sure how much detail I went into on this, but when you're looking at density plots, probably PDFs and things like that are continuous, the y-axis values don't necessarily sum to 1, but the area under there will integrate to 1 essentially. So the above distribution, given our alpha and beta values 31 and 21 they were respectively, looks to be fairly normally distributed in appearance, and we can obtain probabilities of given observations using the PDF and CDF methods for a beta distribution with these shape parameters. So let's do that first. Let's kind of use scipy. We're using stats.beta, and then we're just invoking the PDF methods. So using the PDF, we can find out the probability of observing a value. Say I've just specified one value, x equals 0.66. So we're asking what's the probability of getting an input value of 0.66, which is probably about here somewhere, isn't it, on our, if I got, so probably about here somewhere, value kind of up here maybe, ish, about 4-ish by the looks of that. With our two shape parameters, alpha 31, beta 21. So if we run that, what we see is we get a value of 3.95. That looks a little bit weird, but it's sort of indicating there's about a 4% chance or 4% probability of observing a value of 0.66. So that's exactly that value. Okay. And if I do the same thing again, but let's specify a different value, input value on the x-axis. So I've specified here 0.4, and you can see 0.4 is kind of got a very low probability there. So if we run that, same thing, same parameters, you see we've got like a 0.1% chance of obtaining a probability of observing the value of 0.4. And you can see that there, the kind of like density at 0.4 is very low, the kind of probability. If you inspect our histogram or our kernel density estimator, we can see that the value 0.4 is kind of right in this very low tail of the distribution, and we'll have a much lower probability, as is the case here. So the CDF, the cumulative density function, can also be used to tell us the probability of observing a given value or lower. So we've kind of used the CDF a number of times, and all I'm doing here is I'm replacing the .pdf method with the .cdf method. And we're using the same arguments as when we called the PDF method. We're going to, in this case, we'll ask, what's the probability of getting an x value of 0.66 or less with our alpha and beta parameters of 31 and 21. So let's run that, and we'll see we get a value of 0.825. So we can see there's probably about an 82.5% chance of observing a value of 0.66 or less in our beta distribution. And also if we can do the same using the CDF method for 0.4, like we used the PDF on 0.4, and it was kind of a real low probability. So the probability, now we're asking what's the probability of 0.4 or lower, and what we see is a very a much smaller, less than 1% chance that an observation will have a value of 0.4 or lower. Okay, so that's kind of just stuff we've done before essentially in these videos. We've simulated generated some random data that follows a beta distribution here, interrogated it using the PDF and CDF. So what I was going to do, just to finish this video off, to make it kind of more interesting, to build intuition about the beta distribution, is just a series of plots where I'll change the shape, the values of the shape, so the alpha and beta parameters. So maybe set them to be the same, set them to be different, have alpha bigger than beta, beta bigger than alpha, and see what that does to the shape of the distribution. So what I'm going to do, I'm not going to talk through the plotting code here. I'm just using matplotlib to plot the beta.pdf. But what I'm doing here is I'm setting alpha equal to 0.5 and beta equal to 0.5. So in this case, we've got they're both small, the shape parameters, they're both 0.5. Remember, they've got to be greater than 0, and they're the same. So what we see if we do that is we get this kind of this U-shaped kind of bowl, and the PDF's plotted on the y-axis in this case. But that's the shape of the beta distribution when we use those two shape parameters. When alpha and beta are both set to 0.5. So let's look at something different now, like exactly the same plot, but this time we're going to change alpha to 5 and beta to 1. So we're going to have a higher value of alpha than beta. Let's see what that does to our distribution. Okay, so we now get, like, it almost looks like an exponential function, but it's kind of the inverse of that. So it's highly negatively skewed, and with higher probabilities towards the higher end of the x value scale when we have a higher alpha value than a beta value, and they're both still quite small, I guess, in this case. Okay, let's kind of reverse that and do something different this time, and let's set alpha to 1 and beta to 3. So now we've got, but they're still reasonably small values for the shape parameters, but beta is larger than alpha. And what we see is kind of similar to what the opposite really, but a similar kind of almost this exponential slope type of thing. Similar to when, in this case, alpha was larger than beta, and we got this negatively skewed distribution. This time, beta is larger than alpha, and we get the opposite effect, kind of with higher probabilities to the lower end of the X input scale. Okay, so let's see. We'll set both for this one. We'll set both alpha and beta to 2. See what that looks like. And this starts to get a bit more interesting because we get a parabola shape. We get like this here, kind of inverted U shape. And if we keep increasing these values, so we keep alpha and beta the same, but if we increase them both to 8, what we see is we starts to approximate a much more normal Gaussian distribution there. And let's sort of do the reverse now. So let's do alpha equal to 2 and beta equal to 5. So here we go by setting both reasonably high to 8 or larger numbers, but both the same. We started to get this kind of symmetrical shaped distribution. Let's have a look what happens when we've sort of increasing the shape, the values we're inputting for shape parameters, but now we've got a higher value for beta. And as we saw above, it gives us a positively skewed distribution, but it kind of gives us this what kind of looks like a Poisson distribution really, or something like that. And if we reverse that, let's reverse that now and make alpha 5 and beta 2, and what we should see is this will flip. We'll kind of have a similar shape, but the higher probabilities will be at the opposite end of the scale in this case. And there we see we get the same sort of shape but negatively skewed. Okay, so last one I will do is we'll plot this shape of our distribution with these really high alpha and beta values from the data that we simulated before, and see what that looks like. And as we kind of knew from our KDE and for our histogram, it looks fairly normally shaped, but we haven't set, we've picked large values of alpha and beta, but alpha is still bigger than beta. And what we're seeing that's doing is, as with these other ones here, where alpha was bigger than beta, it's shifting the distribution, the higher probabilities at the higher end of the x-axis scale. So it's kind of shifted the peak or the bulk of the distribution up higher up the x-axis there. Okay, so that's the beta distribution, and you can see is that the beta distribution is kind of it's almost like a family of probability distributions, and if you adjust the shape parameters, it changes the appearance of the distribution. And because it's a continuous distribution, it's particularly flexible at modeling curves with that capture variables or data on a finite interval. Okay, so quite useful and can be used to model lots of different things in the real world. Right, I'm going to stop talking now. That's the end of this video and the end of this kind of series of videos about probability distributions. I hope this was interesting and helpful. Thanks for watching and listening.